Welcome to the deep dive. So you've sent over a really great stack of material. This time looks like excerpts from DBMS M4 DeepDIVE, and it's all focused on database normalization.
That's right. A really fundamental topic.
Absolutely. So our mission here, our goal for this deep dive is really to make sure everyone listening gets a rock-solid grasp of these normalization concepts. Think of it like we're prepping together maybe for an exam or big project, or maybe you just want to finally nail down this part of database design without, getting totally overwhelmed.
Exactly. We want clarity. We'll break down those informal design guidelines first, then get into the nitty-gritty of functional dependencies, Armstrong's axioms.
Equivalence, minimal cover, and then the normal forms themselves, right? 1NF all the way to BCNF.
Hmm.
Plus lossless join and dependency preservation. Got to cover those too.
We've got a lot to cover, but we'll make it make sense. Let's start with those informal guidelines. They're kind of like the first rules of thumb you'd think about.
Okay, good starting point.
Yeah.
What's the first one?
Guideline 1 is all about clear semantics. Basically, every attribute, every column in your table should have a really clear, unambiguous meaning tied to the real world.
Makes sense. Don't be vague.
Right. And crucially, it advises against just lumping attributes for different kinds of things, like different entities or relationships, into one single table. That just creates confusion.
Yeah, the example in the notes shows that perfectly, combining employee stuff like e-name, sesitan, b-date, address, with department stuff like d-number, d-name, dmgrn, all in one big table.
Right. And then you look at address.
You're just thinking, wait, is this the employee's home address or the department's address? It gets messy fast, especially if you're trying to, say, explain this for a test, that ambiguity is a killer.
It really is. The guideline basically says stick to one main concept per table. An employee table for employees, maybe a works-in table for that relationship. Much cleaner.
Avoids headaches later on, which I guess leads right into the second guideline about redundancy.
Yeah. Exactly. Guideline 2, reduce redundant information and, maybe even more importantly, avoid update anomalies. Redundancy is just storing the same piece of info multiple times.
Waste space, obviously.
Waste space, yes. But the bigger danger is inconsistency. And that leads straight to these update anomalies problems when you try to insert, delete, or modify data. They can seriously corrupt your database.
Okay, let's break this down. Good stuff for exam prep here. Insertion anomalies. What's the deal there?
Oh, yeah. An insertion anomaly happens when you can't add data about one thing without also having data about another unrelated thing.
Yeah.
The MPPROJ example illustrates this well.
The one with employee number, project number, hours, names.
That's the one. You basically can't add a new project to the system unless you assign an employee to it right away. And flip side, you can't add a new employee record unless they're already working on a project.
Ah, so it's like a catch-22. You're stuck if you only have half the information.
Precisely. Very frustrating. Then you've got dilution anomalies.
Okay, this sounds bad. Losing data unintentionally.
Exactly. You delete one piece of information and you accidentally wipe out other different information that you actually wanted to keep. The EMPDP example is a classic.
Right, we're deleting the last employee in a department.
It means you lose all information about the department itself. Its name, its manager,
Yes.
gone. Because that info was only stored alongside the employee records.
Wow, okay.
And same idea in MPPRJ. Delete a project, maybe you lose the only record of certain employees who worked only on that project. Or delete the only employee working on a project, and poof, the project details might vanish too.
The Borg headquarters example mentioned is like that too, right? Lose the last Borg drone assigned to headquarters.
And suddenly headquarters ceases to exist in your database.
Yeah.
Not good.
That's
A
weird.
well-normalized design prevents these kinds of accidental data losses.
Okay, and the third type of anomaly, modification.
Modification anomalies. These happen because of that redundancy we mentioned. If you need to change a piece of data that's stored in multiple places,
You have to change it everywhere.
you got it.
Hmm.
And if you miss even one spot, your data is now inconsistent. Think about MBDP again. If Department 5 gets a new manager.
You have to find every single employee row for Department 5 and update the manager info there.
Yes. Miss one, and now some employees report to the old manager, some to the new one, according to your database. Chaos. Same for MPPRJ, changing a project's name means updating it potentially hundreds of times.
Ugh. Okay, so guideline 2 is basically structure your table smartly to avoid these insertion, deletion, and modification nightmares.
That's the core idea. Which brings us neatly to Guideline 3, reducing NOL values.
Ah, NOLs. Always a bit tricky.
They are. Now, NOLs themselves aren't evil. They just mean a value isn't applicable, or maybe it's unknown, or just not available yet.
But having too many can be a problem.
Definitely. They can waste storage space, sure, but they also make it harder to understand what an attribute really means. They can complicate join-and operations.
Like, how do you match on a value that isn't there?
Exactly. And they can mess with aggregate functions like count or SUM in ways you might not expect, something to watch out for in tests.
So the advice is to minimize them. How?
One common strategy is, if you have attributes that are often NLL for many rows, consider putting them in a separate table. You link it back to the original table using the primary key.
Like the office number example.
Yeah.
If most employees don't have an office.
Precisely. Instead of having a mostly NL office number column in your main employee table, create a separate emp offices table. It might just have the employee's SSN as a foreign key and their office number.
So you only store office info for the employees who actually have one, makes the main table cleaner.
Cleaner, more efficient, less ambiguity, good design.
Okay. And the last informal guideline, number 4.
Guideline 4. Avoid spurious tuples.
Spurious, meaning fake or extra.
Extra and incorrect, yeah. These are bogus rows that can pop up when you join tables back together, usually because the tables weren't designed quite right or you're joining on the wrong attributes.
Ah, okay. The example contrasts joining MPLSCS, employee name, project location, and MPPROJ1, SSN, project number, hours, project name, project location, on location. That sounds risky.
It is, because location probably isn't a unique key in either table. So if multiple projects share a location and multiple employees work at that location, joining on location might create combinations of employees and projects that never actually happened. You're generating incorrect associations.
So it's kind of like creating fake data, basically. Like that simplified RABC, R1A, R2BC example shows how joining them can give you extra rows that weren't there originally.
Exactly, you get these phantom tuples. The key takeaway, especially for designing reliable systems or answering test questions, is to design your schemas so that joins primarily happen using primary key, foreign key relationships. That's the reliable way to connect related information accurately.
Got it. PK-FK joins are the way to go. So those 4 guidelines are like our starting intuition for good design.
They are very useful rules of thumb. But to really get rigorous, especially for formal analysis and normalization, we need to dig into functional dependencies, FDs.
Okay, functional dependencies. These sound core to the whole normalization process. What's the essential definition we need?
Okay, so a functional dependency, we write it as XY between 2 sets of attributes, X and Y, in a table.
Mhm.
It basically means that the value of X uniquely determines the value of Y.
So if I know X, there's only one possible value for Y associated with it.
Precisely. More formally, if you take any 2 rows, let's call them T1 and T2, in your table, and if they have the same value for the attribute set X, so T1X, T2X, then they must also have the same value for the attribute set Y. T1Y equals T2Y.
Okay. Like your example, SSN, ename. Give me an SSN, there's only one possible employee name. Makes sense. SSNs are unique.
Exactly. And these FDs aren't just made up. They reflect real-world rules and the meaning behind the data. Like P-number, P-NIM-4. Location of project number determines the project's name and location. Or SSN, P-number hours. An employee working on a specific project works a specific number of hours on it. Understanding why these dependencies exist is key.
Right. And what about when it's not an FD? The notes show an example where A1 and attribute A maps to both B1 and B2 and attribute B. That breaks the rule.
Absolutely. A1 doesn't uniquely determine a single B value, so AEB does not hold in that specific data instance.
But interestingly, in the same example, BA does hold, because B1 only maps to A1, B2 only maps to A1, and B3 only maps to A2. Each B value has only one corresponding A value.
Correct. And when BA holds, we use various terms. B functionally determines A is functionally dependent on B, A is functionally determined by B. It all means the same thing. You'll see these phrases used interchangeably in textbooks and exams.
The employee dept exercise helps make this concrete. ED, name employee ID, determines name. That probably holds. ED is usually a primary key.
Likely, yes.
And DNO, name lock department number, determines name and location. Again, likely true. Department numbers are usually unique.
Right.
But a name ED, probably not, right? You could have 2 employees named John Smith.
Unlikely to hold in most real systems, correct.
And something like age a name, definitely not. Lots of people have the same age but different names. These really show how FDs capture those real-world uniqueness constraints.
That's a critical point to remember, especially for tests. Functional dependencies are properties of the schema, the underlying design and rules, not just what data happens to be in the table right now.
So just because it looks okay now doesn't mean it is okay.
Exactly. The teacher course example is perfect. Maybe in your current small data set, every teacher only teaches one course. But you can't just declare teacher course as an FD because you know the real-world rule is that teachers can teach in multiple courses. The FD has to hold for all possible valid data, not just the current snapshot.
Okay, so we can't automatically infer an FD just by looking at data, but we can use the data to disprove an FD, right? If we find just one counterexample.
Absolutely. If you find two rows where X is the same but Y is different, then XY is definitively not a valid FD for that schema. The RABCD example demonstrates this finding specific rows shows that AE, B, BAA, and DC cannot hold as FDs for that relation based on that data. A single violation kills the potential FD.
Got it. Proof by counterexample works for disproving FDs. Now, the notes mention different types of FDs. Trivial, non-trivial.
Right. It's a useful distinction sometimes. A trivial FD is one where the right-hand side, the dependent, is just a subset of the left-hand side, the determinant, like AEA or ED, a name.
Okay, so trivial ones are kind of obvious. They don't tell you much new. If I know your ID and name, I obviously know your name.
Precisely. They hold by definition. A non-trivial FD is where the dependent is not a subset of the determinant, like role, know, and name. These are the ones that actually tell us something interesting about the relationships in the data.
They reveal structure.
Yes. And then there's semi-non-trivial, which is kind of mixed, like AB, ABC. The B part is trivial, B is in AB, but the A determining C part, if A alone doesn't determine C, could be non-trivial. It's less commonly discussed, but good to be aware of the classification.
Okay, so we have FDs. We know what they mean, different types. How do we work with a whole set of them? That leads us to Armstrong's axioms, right? These sound important.
Extremely important. Armstrong's axioms are a set of inference rules for functional dependencies. Think of them as the basic logical rules that let you figure out all the other FDs that must be true if your initial set of FDs is true.
Okay. And they are sound and complete. What does that mean exactly?
Good question. Sound means that any FD you derive using these rules is guaranteed to be logically correct. It will hold true in any database state that satisfies your original FDs. You won't derive anything false. Complete means that every single FD that is logically implied by your original set can be derived using just these rules. You won't miss any implied dependencies.
So they give you a guaranteed way to find everything that logically follows from your starting FDs. That collection of all implied FDs is called the closure, F plus day.
Yes, F plus is the closure of F. The set of all FDs logically implied by F. Armstrong's axioms give us the mechanism to find F plus. Mastering these is key for deeper normalization understanding.
All right, let's hear them. What are the primary axioms?
There are three core ones. First, reflexivity. If Y is a set of attributes that's a subset of X, then XY always holds. That's kind of the basis for trivial FDs.
Okay, if I know X, I know any part of X. Makes sense.
Second, augmentation. If XY holds, then adding the same set of attributes Z to both sides means XY also holds. Knowing more doesn't invalidate what you already knew, determines something else.
Right. If SSN determines name, then SSN and higher date still determine name.
Exactly. And third, transitivity. This is a very intuitive one. If XY holds and YZ holds, then XEZ must also hold.
Ah, like a chain reaction. If the employee ID tells you the department number and the department number tells you the department manager, then the employee ID indirectly tells you the department manager.
Perfect analogy. Those are the three foundational axioms. From them, we can derive other useful rules.
Like the secondary rules mentioned, union, decomposition, are they just shortcuts?
Pretty much. They follow logically from the first three, but they're often handy. Union. If XY and XZ, then you can combine them into XYZ. Decomposition, the reverse. If XYZ, you can split it into XY and XUZ.
Okay, combine or split the right-hand side if the left side is the same.
Yep. Then there's pseudo-transitivity. If XY and WYZ, then WXEZ, it's like a modified transitivity.
Right.
And composition. If XY and ZW, then XZ, XYW, combine the left sides and combine the right sides. Knowing these can speed up figuring out implied dependencies.
Okay, that's a powerful toolkit. How does this connect to finding keys? You mentioned attribute closure earlier.
Right. Attribute closure is directly related. The closure of a set of attributes X, written as X plus A, is the set of all attributes that are functionally determined by X, using a given set of FDs, F, and applying Armstrong's axioms, or the derived rules.
So everything you can figure out if you only know the value of X. How do you calculate it?
There's a straightforward algorithm. You start with the attributes in X itself. Then you look at your FDs. If you find an FD like AEB and all the attributes in A are already in your current closure set, you add B to the set. You keep repeating this, checking all FDs against your current set and adding determined attributes until you can't add any more attributes in a full pass.
The example RA, BCD with FDS, AB, BEC, D makes this clear. To find A plus,
You start with A.
okay, AB is in F, A is in our set, so add B. Now we have AB,
Good.
BC is in F, B is in our set, so add C. Add
So
BC, CD is in F, C is in our set, add D. Now AB, CD, DA is in F, D is in our set, A is already in the set, so we can't add anything new. A plus is A, B, C, D.
Exactly. And since A plus contains all attributes of the relation R, A is a superkey. Since A is just a single attribute, it's minimal, so A is a candidate key.
And doing the same for B, C, and D in that example also gives A, B, C, D, so they are all candidate keys in that specific case.
Correct. The second example, RVWXYZ, shows computing closure for multi-attribute sets like XY, VXY, WXY, and using that to determine if they are candidate keys. It's a fundamental skill. Computing closure lets you find keys.
Okay, that's clear. Now, what about comparing different sets of FDs? The notes talk about equivalence and minimal cover.
Right. Sometimes you might have two different sets of FDs, say F and G, that actually describe the exact same set of constraints, just maybe written differently. We say F and G are equivalent if their closures are identical, meaning F plus equals G plus plus. Every FD implied by F is also implied by G and vice versa.
How do you check that? You mentioned covering.
We say F covers E if every single FD in E can be derived using the FDs in F. To check this, you take each FDXUY from E, calculate the closure X plus using only the dependencies in F, and then check if Y is a subset of that calculated X plus. If this works for all FDs in E, then F covers E.
So for F and G to be equivalent, F must cover G, and G must cover F. You have to check both ways.
Exactly right. The example showing F, A, E, C, A, C, A, E, D, E, A, A, G, E, H, E are equivalent means you'd have to perform those checks.
And the other example with RABCD and comparing FD1, FD1, FDD with FD2, FD2, ABD, ACACA involves showing FD1 covers FD2 and FD2 covers FD1 step by step using closure calculation.
Yes, that process demonstrates the check for equivalence. Now, related to this is the idea of a minimal cover, sometimes called a canonical cover.
Minimal meaning simplified, the smallest possible set.
Essentially, yes. A minimal cover F for a set of FDs E is an equivalent set, so F plus E plus, that satisfies three specific conditions of minimality. It's like boiling the dependencies down to their simplest non-redundant form.
Okay, what are those three conditions we need to know for finding one?
First, every FD in the minimal set F must have only a single attribute on the right-hand side. So if you have A, B, C, you'd split it into A, B, and AC. This is the standard or canonical form.
Okay, one attribute on the right.
Got it. Second, for every FD X, A, and F, you cannot remove any attribute from the left-hand side X and still have the dependency hold, meaning there are no redundant attributes on the left-hand side. If Z is a proper subset of X, then the set of FDs formed by replacing XA with Z is not equivalent to the original set F.
So every attribute on the left is truly necessary.
Correct. And third, you cannot remove any entire functional dependency from F and still have a set that's equivalent to the original, meaning there are no redundant functional dependencies in the set. Each one is essential.
Makes sense. Single attribute on the right, no extra attributes on the left, and no extra dependencies overall. The example converting E, BA, DA, AB into the minimal cover BD, DA must follow these steps.
It does. You'd first check condition 1, already met, then check condition 2, look at A, B, E, can we simplify the left side? You'd compute B plus using E. If a D is in B plus S, then ADD can be simplified to BED. In this case, B plus using E would include A from BA and then D from DA. Oops, no, maybe from ABD. Let's recheck logic. The example derives BD somehow, maybe implicitly using transitivity after simplifying. The example says the result is BDDA. Let's assume we check B plus under BADAD, P plus BA. Now check AB plus ABD. Since A alone doesn't give D and B alone gives B, AD is necessary for D initially. The example explanation might be simplified. Let's rethink. The process usually involves 1. Standard form, split RHS. 2. Minimize LHS for each XA. Check if any attribute in X is redundant by checking if XZ plus includes A using the current set of FDs. 3. Remove redundant FDs for each XA. Check if it could be derived from the other FDs in the set. Maybe the ABD simplifies to BD because BA hold, and maybe another implicit step. Let's stick to the principle. Ensure no LHS attribute is redundant.
Okay, the principle is key. Remove redundant attributes on the left. Then the third step, removing redundant dependencies.
Yes. For the third step, you take each dependency remaining after step 2, say XEA, temporarily remove it, and then check if you can still derive A from X using the other dependencies left in the set. If you can, then XEA was redundant, and you remove it permanently. The example states BAA ends up being redundant, presumably because you can get it from the final set, BEED, via transitivity.
Okay, so it's a systematic process. Standard form, minimize left sides, remove redundant FDs. Finding this minimal cover gives you the essence of the dependencies.
Exactly. And it's often a prerequisite or a helpful step for normalization algorithms, which brings us to the main event, the normalization process itself.
Right, normalization, taking our relations and making them better, less redundant.
Precisely. It's the process of analyzing relation schemas based on their functional dependencies and primary keys to achieve desirable properties. The goal is usually to minimize redundancy and eliminate those insertion, deletion, and modification anomalies we discussed.
And we measure how good a relation is using normal forms, right?
Yeah.
1NF, 2NF, 3NF, BCNF.
Yes. Each normal form represents a condition or a set of criteria that a relation must meet. Generally, higher normal forms, like 3NF or BCNF, are considered better designed than lower ones, like 1NF or 2NF.
The material mentions 4NF and 5NF too, but maybe less common.
They deal with more complex dependencies beyond FDs, called multi-value dependencies and join dependencies. Important for advanced design, but 3NF and BCNF cover the vast majority of issues related to FDs. We'll focus there.
And when we decompose tables to achieve these forms, we need to worry about lossless join and dependency preservation.
Absolutely critical. We want to break tables down without losing information, lossless join, and without losing the ability to enforce our original rules easily, dependency preservation. We'll get back to those. First, let's define some key terms needed for the normal forms themselves.
Okay, quick review.
A superkey.
A set of attributes that uniquely identifies a tuple.
Key or candidate key.
A minimal superkey. Can't remove any attribute and still have it be a superkey.
Primary key. The candidate key chosen by the designer as the main identifier.
Secondary key.
Any other candidate keys that weren't chosen as primary.
Prime attribute.
An attribute that's part of any candidate key.
And non-prime attribute.
An attribute that is not part of any candidate key. Perfect. Knowing these terms is essential for understanding the definitions of the normal forms.
All right, let's hit them. First, normal form, 1NF. What's the rule? Seems like the most basic one.
It is. 1NF basically says two main things. First, the domain of every attribute must contain only atomic values that are indivisible from the database's point of view. Second, every attribute in a tuple must have only a single value from its domain.
So no multi-valued attributes, like storing multiple phone numbers in one field, and no composite attributes treated as a single unit if you need to access parts. No repeating groups.
Exactly. You can't have lists or sets stored within a single attribute cell. If you have, say, multiple locations for a department, you wouldn't put them all in one locations field. You typically create a separate table, like depth locations, to handle that one-to-many relationship, ensuring each cell in your original department table and the new table has only one atomic value. Most relational databases enforce this inherently anyway.
Okay, 1NF is mostly about table structure and atomicity. What about second normal form, 2NF?
2NF builds on 1NF and tackles redundancy that arises from partial dependencies. First, we need the idea of a full functional dependency.
Right, we touched on this. XUI is a full FD if you can't remove any attribute from X and still have the dependency hold.
Correct. The classic example is SSN, phi number hours. Presumably, you need both the employee's SSN and the project number to know the hours they work on that project. Neither SSN alone nor P number alone is enough. That's a full dependency.
Whereas SSN, P number in name, would likely be a partial dependency.
Probably, because SSN in likely holds on its own. The me number part is unnecessary to determine INDI.
Okay, so how does this relate to 2NF?
A relation is in 2NF if it's in 1NF, and every non-prime attribute is fully functionally dependent on the primary key.
Or the other way to phrase it, no non-prime attribute should be dependent on just a part of any candidate key.
Exactly. If you have a non-prime attribute that depends only on a portion of a composite key, you have a 2NF violation. You fix it by decomposing, pulling out the partially dependent attribute along with the part of the key it depends on into a new table.
Got it. Moving up to third normal form, 3NF. What's the extra condition here?
3NF builds on 2NF and eliminates redundancy caused by transitive dependencies.
Transitive, meaning indirect. Like A determines B and B determines C, so A indirectly determines C.
Precisely. A transitive dependency exists if you have a non-prime attribute C that depends on another non-prime attribute B, which in turn depends on the primary key A. So A, B, and B, C, where A is the key, and B and C are non-prime. This creates redundancy because the relationship between B and C is stored repeatedly for every A that relates to B.
So 3NF says be in 2NF and have no transitive dependencies of non-prime attributes on the primary key.
That's one way to state it. The more general and often more useful definition for checking is a relation R is in 3NF if, for every functional dependency XUY that holds an R, at least one of the following is true.
Okay, what are the conditions?
Either 1X is a superkey of R, or 2Y is a prime attribute of R, meaning every attribute in Y is part of some candidate key.
Okay. So any dependency is fine if the left side determines everything is a superkey, or if the right side is part of a key anyway. The problematic ones for 3NF are when a non-key determines another non-key.
That's the essence of it. If you find an FD where X is not a superkey and Y is not prime, you have a 3NF violation, likely due to a transitive dependency.
Right. And then there's Boyce-Codd normal form, BCNF, stricter than 3NF.
Yes, slightly stricter, often called 3.5NF. It closes a loophole sometimes left by 3NF. The rule for BCNF is very simple. The relation R is in BCNF if for every non-trivial functional dependency, X, Y that holds in R.
Let me guess. X must be a superkey.
Exactly. X must be a superkey, full stop.
So it removes that second option from the 3NF definition, the one that allowed the dependency if Y was a prime attribute.
Correct. In BCNF, if the left side X isn't a superkey, the dependency is a violation, regardless of whether Y is prime or not. 3NF allows X, Y if Y is prime, even if X is a superkey, but BCNF does not.
The example, adding area, county name, where county name is prime but area isn't a superkey, highlights this. That relation might be in 3NF but would violate BCNF.
Precisely. BCF is conceptually simpler. The left side of every determinant must be a superkey. It eliminates certain subtle redundancies that 3NF might allow.
Okay, so BCNF is the strictest based on FDs. Now, we decompose to get into these forms, but we need to make sure the decomposition is good, right? Lossless join and dependency preservation.
The two golden rules of decomposition. When we split a table R into smaller tables, R1, R2, etc., we absolutely need two properties. First, attribute preservation. Every attribute from the original R must appear in at least one of the new tables, R1, R2. That's usually easy to ensure.
Okay, don't lose any columns.
Second, the lossless join property. This means that if we join the decomposed tables R1, R2 back together using natural joins, we should get exactly the same set of tuples as the original table R. No extra spurious tuples and no loss of original tuples.
So we can break it apart and put it back together perfectly. The ROABC into R1AB and R2BC example shows this might be lossless or not, depending on the FDs. There's a formal test, too.
Yes, there's an algorithm using a matrix representation of the decomposition and applying the FDs to see if you can eventually derive a row of all A symbols, indicating the join is lossless. It's a bit involved for audio, but it's a formal check.
Okay, so lossless join is crucial to not mess up the data itself. What about dependency preservation?
Dependency preservation means that we can still check and enforce all of the original functional dependencies F by looking only at the individual decomposed tables, R1, R2, etc., without having to perform expensive joins between them just to validate a rule.
So if we had A, E, B originally, and A and B end up in the same decomposed table R1, that dependency is preserved easily. But if A is an R1 and B is an R2, we might have lost the ability to check it efficiently.
That's the idea. Formally, a decomposition preserves dependencies if the union of all FDs that hold within each individual re, when you take the closure of that union, is equivalent to the closure of the original set F, F+. If you need to join tables to check an original FD, the decomposition is not dependency preserving.
Why is that so important? Just for efficiency?
Primarily efficiency and ease of maintaining integrity. If checking a simple update requires joining multiple large tables, it can kill performance and makes ensuring data consistency much harder. You want constraints to be checkable locally within a single table whenever possible.
The RABC with FDCAB decomposed into R1AB and R2BC example is good. It's lossless and dependency preserving. AAB is checkable in R1, BC is checkable in R2.
Yes, that's an ideal decomposition. Both R1 and R2 are also in BCNF in that case. The notes also show how to check for BCNF violations. Is the determinant X a superkey? Check if X plus contains all attributes, and outline the algorithm. Find the BCNF violation XY, split the table into R1XY and R2RY, and repeat.
The class relation example decomposing into course, classroom, and section shows that process driven by FDs to get BCNF tables.
It does, but here's the catch, and it's a really important one for practical design and maybe tricky exam questions. You cannot always achieve both BCNF and dependency preservation.
Oh. You might have to choose.
Sometimes, yes. The classic example is RJK with FDS, JKL, The dependency LUK violates BCNF because L is not a superkey. J is needed too. To get BCNF, you decompose into R1LK and R2JL. This decomposition is in BCNF and is lossless join.
But
But the original dependency JKL cannot be checked using R1 or R2 alone. You'd have to join R1 and R2 to enforce it. So this BCNF decomposition is not dependency preserving.
so in that case, you'd have to decide, do I want pure BCNF and accept the difficulty of checking JKL, or do I maybe stick with 3NF, which the original relation might have been in, to keep all dependencies easily checkable?
Exactly that trade-off. Often, preserving dependencies is considered more critical in practice, so designers might intentionally decompose only to 3NF if a BCNF decomposition would lose dependencies.
Wow, okay, that's a key practical consideration. So let's try to wrap this up. In this deep dive, we've really gone through the whole process. We started with those informal guidelines, clear semantics, less redundancy, fewer NULs, no serious tuples.
Intuitive starting points.
Then we dug deep into functional dependencies, what they are, how they come from the real world, the different types, and crucially, Armstrong's axioms for inferring all implied dependencies.
Finding the closure F plus board, and calculating attribute closure X plus to find keys.
Right, and understanding equivalent sets of FDs and how to find a minimal cover.
Simplifying the dependencies.
Then we tackled the normal forms themselves, 1NF, 2NF, 3NF, and that stricter BCNF, understanding the rules for each.
Eliminating partial and transitive dependencies and ensuring determinants are keys.
And finally, the crucial goals of decomposition, making sure it's a lossless join so we don't corrupt data, and aiming for dependency preservation so we can still enforce our rules easily.
And acknowledging that sometimes, especially with BCNF, you might face a trade-off between the highest normal form and preserving all dependencies.
It really feels like understanding all these pieces is fundamental if you want to design databases that are actually efficient, reliable, and, don't cause constant headaches with bad data. Avoiding those anomalies is key.
Absolutely. This provides the theoretical foundation. Whether you're facing an exam or designing a real system, knowing these principles lets you make informed decisions and build much better databases.
And definitely gives a solid base for anyone wanting to look into even more advanced stuff like 4NF or 5NF later on. So here's a final thought for everyone listening to mull over, building on that trade-off we just discussed. Considering that tension between, say, BCNF and dependency preservation, can you think of specific real-world situations where you might deliberately choose to keep a database schema in 3NF, even if you know it's not technically in BCNF? What factors would drive that practical decision?
Something definitely worth pondering. Thanks for diving deep with us today into the world of database normalization.